So in our last video, I took this beam with a distributed load and a point load and created a free body diagram and solved for the reaction forces on the free body diagram. What we're going to do now is we're going to take that free body diagram and use the information to create a shear and a moment diagram. So the deal with the shear diagram is that it follows the forces on the free body diagram. And so the one difference is that this force here we had to consolidate into an equivalent point load. But when we create the shear diagram, we're going to look at it as if it's a distributed load again, as opposed to as if it's a point load. So what we do is we start off over on the left-hand side and take a look at the free body diagram, and we see that we start with AY going up by 1350. So that on our shear diagram here is going to go right up to right about there, so straight up by 1350. And so that is that first piece there. Then, because we have a distributed load, what happens is that distributed load pushes down by 200 pounds per foot. So what that means is that for every foot, we go down by 200 pounds. 3 feet in, we have that point load happening. So let's figure out where we are at 3 feet in. So 3 times the negative 200 pounds per feet is what this line is going to look like. And so the amount that we go down by is just going to be 3 times 200 pounds per foot, or 600 pounds, because that was 3 feet that we started off with there, times 200 pounds per foot. So that's how far we've gone down. So we've gone down by 600 feet. So 1350 minus 600 is going to give us our next point on this diagram here, which is going to be 750, which is right about there. Okay, so this point here is 750, and that's our first stretch of our first free body of our shear diagram. And then at this point, we look up at our free body diagram and we notice that there's a point load dropping us down an additional 500 pounds. So 750 minus 500 pounds, that is going to bring us right down to 250 pounds. All right, so these are each in pounds. And then from there, we go back to just mapping the distributed load. So for every foot, we go down an additional 200 pounds. And so we don't have anything else going on for the rest of the distributed load until we get to the very end. So we have 7 feet at 200 pounds per foot. So 200, 200, 200, and 200, so on for 7 feet. And so let's see where that brings us down to here. So basically, this number here should be the 250 that we're starting at minus 7 feet of a distributed load of 200 pounds per foot. All right, so that works out to be, it should work out to be right at that 1150. And the reason that I know that is I'm kind of cheating and I'm just looking at this here. And I know that, sorry, you can't see that. I know that we need to end up with 1150 pounds to return to zero here. So if you put that into your calculator, you should find that that is actually 1150 pounds. And that tells us how far we need to go down additionally after we've gone down to there. And so we can go all the way down to right about there. And then the last piece, looking at our free body diagram, is we need to pop back up by 1150. And so this one here should be negative 1150. And so then we add on this last vector going straight up, the reaction force at B, and that should bring us back to zero because we add on that 1150. And that is our shear diagram.